All right. Um, Good afternoon, IB Physics class. I hope you're doing well. I'm doing all right. I picked up Animal Crossing the other day, and I got a really large book that I'm working my way through. That's pretty good. If you haven't read anything by Neil Stephenson, he's pretty good. All right. So today what we're going to focus on is what were we going to focus on today? I have to remember. So the first thing I wanted to talk about is how to describe a nucleus. Describing a nucleus. What is the book about? You know, it's funny you should ask that because it's about a malware attack. So, computer virus on a mass, like an MMORPG video game type thing. So that's what it's about. So far, I'm only about 200 pages in, and it's 1,000 pages. So how do we describe a nucleus? Well, let's suppose we have a nucleus. I'm going to call it X, and X would be the element symbol. Okay. So the element symbol, if you recall, it could be like hydrogen or helium or lithium or, boron or whatever it is. Okay. As a superscript, we're going to put a number A. And A is called, it kind of has two names. We could call it the mass number, or we could call it the Nucleon number. So a nucleon is by the way, this suffix on, anytime you see that suffix, that means a type of particle. Okay, so for example, a photon is it's a particle of light. An electron, it's a particle. A proton, a neutron. Okay, so the on suffix means a type of particle, and so a nucleon is just a particle that is inside the nucleus. Okay, and what are the particles inside the nucleus? It is the protons and the neutrons. So a proton is called a nucleon, and a neutron is also called a nucleon. All right. So A is the nucleon number, which is how many protons and neutrons does it have? Okay, does the nucleus have? And then as a subscript, we write Z, and Z is the atomic number, which is basically, it is the number of protons in the nucleus. Okay. So I think it's pretty obvious that the nucleon number is equal So the number of protons and neutrons in the nucleus is equal to the number of protons plus the number of neutrons. Okay? Number of protons plus the number of neutrons. So we could write this. Number of protons is the atomic number, Z, and the number of neutrons, we just call it N. So Z plus N equals A. All right, so that's an equation for you. Okay. If we're talking about a specific nucleus, so a nucleus with a certain composition of protons and neutrons, so a specific one is called a nuclide. Okay, so sometimes I'll throw that word around, nuclide, and when I say that, I mean a specific nucleus. So let me give you an example of a specific nucleus. Let me look in my book here. By the way, I'm looking at my basic nuclear engineering book, which is a handy dandy book. So let's suppose we had a nucleus like radium 22688, like that. So that's radium. So, and what if I wanted to know how many neutrons? So how many protons does this nucleus have, first of all? It has 88 protons. That's just the atomic number. All right. If we want to know how many neutrons it has, that's going to be the total number of nucleons the number of neutrons it has is the total number of nucleons, which is 226, minus the number of protons, which is 88. So that's going to give 112, 130, 138, I believe, neutrons. So that's 138 neutrons for that. Okay? Notice that the symbol for the element is not really essential. Okay? It is... So really all the information we need about the nucleus is given by its... all the information we need is given by the number of protons and the total number of nucleons. So I don't even care about this so much. All right? If you don't know the name of the element, that's fine. All I care about is the number of protons and neutrons. It's possible to have a nucleus, maybe radium 88 225. So this one has the same number of protons, so it's still radium, but it has a different number of neutrons. See how it has one less neutron? Okay. This is called an isotope. So an isotope has the same number of protons, but a different number of neutrons. Okay. Now, oftentimes it's the isotopes that are unstable. Yesterday I was talking about radioactive decay, and it is oftentimes the isotopes of an element. Usually there's only a couple of isotopes that are stable, and then the rest are unstable. Okay. Here's something that's interesting. If you look at the number of neutrons, it's greater than the number of protons. So as the atomic number increases, you tend to need more and more neutrons for stability. I'm going to show you an interesting graph from my book here. I'm going to put it under the... Okay. So if we look at this, this is a graph of number of neutrons versus number of protons. And this line right here is the line y equals x. So this is the line where number of neutrons equals number of protons. So you can see that the observed nuclei, the observed nucleuses that we see in nature are above this line because they have more neutrons than they have protons. Okay? So I think that's kind of interesting. All right. So now we can also write the types of radiation in this way. Okay. Let me adjust here. So looking at the different types of radiation that oh, wait a second, I have a good question. What is the unit of weight for mass number? Is there a weight difference between protons and neutrons? Excellent question. We're going to talk about that tomorrow. But right now we're just counting the amount. So these are just integers. There is no unit. How do neutrons offer stability? That's another really good question. If you think about a nucleus, it has a lot of positive charge in it from all the protons. And the positive charges want to repel each other, likes repel. So the nucleus kind of wants to explode, and so you need something to hold it together, and that's what the neutrons are. The neutrons are involved with what's called... Okay, so looking at the types of radiation, so the types of radiation are alpha particle, and an alpha particle we said was a helium nucleus, and a helium nucleus had 2 protons and 2 neutrons. So an alpha particle is 2, 4. All right. There was a beta minus, which was an electron, okay, which has a charge of -1. So it's kind of like an electron almost has atomic number -1. And it's not a nucleon because it's outside the nucleus. So its nucleon number is 0. Okay. A beta plus has a charge of +1, and it has a mass of a nucleon number of 0. A gamma ray, which was a photon. Photons have no charge and they're not in the nucleus, so they're just 0, 0. What do you think a neutron would be? Well, neutrons, they have no electric charge, so a neutron kind of has atomic number 0. Okay. But it is a nucleon, so it's 1, 0. Okay. And lastly, what about a proton? Protons have a charge of +1, and they are a nucleon, so they're 1, 1. So these are the different types of radiation. I didn't talk yesterday about neutrons being a source of a type of radiation, but they are. Remember that graph that I showed you just now, how you have more neutrons than protons? So because we have this sort of excess of neutrons, they tend to want to pop off when you have an unstable nucleus. So you get a lot of neutron radiation. Because neutrons have no electric charge, just like the gamma rays, they're able to penetrate through materials quite easily. And so neutrons are also a very dangerous form of radiation. So these two are the most dangerous forms of radiation from outside your body. All of them are dangerous if you have a source inside your body, but outside. These two are the most dangerous. Okay, so let's talk about nuclear reactions. Okay, so let's go with. I'm going to look at my book here. I really like having this book because it has an appendix which tells me how all the different so I'm going to put this underneath the okay. So I don't know if you guys can read that or not. Maybe I'll move it up a little bit. Look, you can see in this table here that I've got potassium, and it says the half-life. See how half-life? And it says the half-life of this version of potassium is 1.2 times 10 to the 9th years. That's 1.2 billion years. That's a long time. So it also has a type of decay. So it tells you how these different particles are decaying. So you can see a lot of them are beta minus, some of them are alphas, some of them are beta pluses. So there's all kinds of different so-called decay modes. All right. So what if I started with potassium 40? Okay, which would be K 4019, and it becomes something. So I want to know what is that thing that it becomes. And if I look up the decay mode, it's beta minus decay. All right. So beta minus decay means that it's this thing is spitting out a beta minus particle, which is 0, -1. So how can we figure out what is the identity of this unknown? What does the potassium become after it spits out a beta minus? All right. To do that, we're going to use conservation of nucleon number and conservation of charge. Okay, so these are the two rules. Conservation of A and conservation of Z. So if we look at it, the reactants, for conservation of A, the reactant has 40 nucleons. So we start out with 40 nucleons. The two products have an unknown number of nucleons here, so I'm just going to write that as A. And then the beta minus has 0 nucleons. So what that tells us is that A equals 40. Okay? So this is 40. Conservation of Z, charge. We can see that the reactant has 19, a charge of 19. This one has an unknown charge, so I'll write it as Z. This one has a charge of -1, so we have plus -1. And that says that Z equals 20. Okay? And that tells us how many protons and how many neutrons are in this nucleus after the reaction takes place. Okay? And if you, I don't care what, you can just leave this as a question mark, but since I have the information right here in my book, I can see that the element with 20 protons is calcium. So I could write that as calcium in retrospect. Okay? Let's do like 1 or 2 more of these and then I'll be done. How about, let me find one. How about polonium? Polonium, which is atomic number 84. Let's think about polonium 208. Okay. This polonium 208 has a half-life of 2.93 years. And it decays by alpha. This is called alpha decay. It spits out an alpha, which is 4,2. And so I want to know, what is the byproduct after polonium 208 decays via alpha decay? So again, using conservation of nucleon number, I have 208 equals 4 plus the unknown. Okay. And so that tells me the unknown nucleon number. So that tells me that the unknown nucleon number is 204. So this is 204. And then conservation of charge tells me that 84 equals 2 plus Z. So that means that Z equals 82. So this is the number of protons and then the number of nucleons for this product of the polonium decay. And it turns out that the identity of the element with 82 protons is lead. Okay, so polonium turns into lead. In some sense, nuclear engineering is alchemy, because remember, alchemists were trying to turn things into gold. And so we actually have elements that are changing from one type to another. Let's do one more, just for fun. Let's do this reaction. Uranium 235 92 plus a neutron, which is 1, 0, becomes I'm sorry, class. Krypton 3685 plus an unknown plus 3 neutrons. Okay? So we want to figure out what is the unknown. Well, so this has more than one reactant and more than one product. Okay? So if we figure this out here, conservation of mass number, conservation of nucleon number, we can see that on the left-hand side we have 235 and we have the neutron. So on the left-hand side, our total nucleon number is 236. And then here we have 85 nucleons, an unknown number of nucleons, and then this is 3 neutrons, so that's actually 3 nucleons. So we have 88 plus the unknown number of nucleons. Okay, so subtracting those from each other, 236 minus 88 equals 148. A equals 148. So this has 148 nucleons. And then conservation of charge. This has a charge of 92. This has a charge of 0, so the total amount of charge is 92. Here on the product side, we have 36 plus an unknown plus 0 charge. So we have 36 plus Z. So that gives Z equals 56. So this unknown isotope has 56 protons and 148 nucleons total. So let's figure out which one is that. Looking at the periodic table, I want to say it's bromine, but I'm not positive. 6. Oh, barium. It's barium. I knew it started with a B. So that's the identity. All right. So this is how you do problems with nuclear reactions. I might ask you to predict the product of the reaction. I have a question here. Why are alpha particles specifically helium? The reason that alpha particles... now, keep in mind, an alpha particle is a helium nucleus. It doesn't have the electron cloud around it. But the reason that alpha particles are a type of radiation is just because it's a common thing for unstable nuclei to spit off. Okay? This, and thank you for asking that question. That brings up a good point. This type of a decay, this is called fission. Because if you notice here, anytime an unstable nucleus like uranium breaks into 2 big chunks, it's not really like alpha decay or beta decay or gamma decay. It's just like it broke into 2 pieces that are sizable. That is called fission. Okay? So that's the end of my lesson today. And tomorrow we'll get to the answers to some of the other questions I saw in the live stream. And thank you for watching. I hope you have a good rest of the day. Bye.